So hello everyone, my name is Anmol Saini and I am your chemistry SME, and today we are solving BPT 17 chemistry questions. Okay, so let's start. Okay, this in this BPT we have D and F block element chapter. So first question is, which of the following pair have almost similar size? And our option are Ti. This is titanium 22 and zirconium 40 atomic number, niobium and tantalum, yttrium and lanthanum, calcium or iridium. Okay, so for this type of question, uh, we will have to know the concept of lanthanoid contraction. What is lanthanoid contraction? Lanthanoid contraction is nothing but it is a gradual decrease in atomic radii. This is due to the increase in atomic number and poor shielding of 4f electron. Poor shielding of 4f electron. Poor shielding of 4f electrons. Okay. So due to the lanthanoid contraction, niobium and tantalum have almost same size. Okay. Niobium and tantalum have similar atomic and ionic size due to the lanthanoid contraction affecting the element in the group in the same group but different period. Okay, so due to the lanthanoid contraction, there is a decrease in atomic and ionic radii in the lanthanoid series or lanthanoid series. Okay, so this is easy question. So correct answer is second. So let's come to question number 52. Here we have to match the accept with the metals. Okay, with the given metals. So first condition is the metal which reveals a maximum number of oxidation state. And here we have given with the 3D series element, or you can say 3D transition series element. So we have scandium, we have copper, we have manganese, and we have zinc. As we have studied that manganese has a maximum number of oxidation state which range from +2 to +7, +2, +3, +4, +5, +6, +7. So the maximum number of oxidation state will be shown by manganese. So A3. So the correct will be A or B. Okay? So the next part, the metal, although placed in the 3D block, is considered not as a transition element. It is a very famous statement from NCRT book that the element is placed in 3D series but not a transition element. So it is zinc. Okay. So 4. So A will be correct answer. Okay. So let read option C. The metal which does not exhibit variable oxidation state. The metal which does not exhibit variable oxidation state. Scandium does not exhibit variable oxidation state because the most stable state is scandium +3. Okay. The metal which in +1 oxidation state in aqueous solution undergo disproportionation reaction. And this is copper. Copper undergo disproportionation reaction like this. Copper plus in aqueous will go to Cu2 plus aqueous and Cu, copper solid. Here oxidation state of copper is 0 and here oxidation state of copper is 2 plus. And this is the given reaction. Undergo a disproportionation reaction in aqueous solution. And scandium has a only one stable oxidation state, that is +3. So the correct option is A. Okay. Now comes to question number 53. Question number 53 is saying identify the incorrect statement from the following. We have to identify the incorrect statement. Okay. So first statement is lanthanoid reveal only +3 oxidation state. No, lanthanoid can show oxidation state from +2, +3, +4, but the most stable state is +3. But it can also show +2 and +4 oxidation state. So this is the incorrect. So the first one is incorrect. But we have to check the other option as well. The lanthanoid ion other than F0 type and F14 type are all paramagnetic. Yes, this is correct because except F0 and F14, all the lanthanoid ion will have an unpaired electron. And when they have unpaired electron, they will show color. Or you can see when they have unpaired electron, they are paramagnetic. Okay. So statement 2 is correct. The overall decrease in atomic and ionic radii from lanthanum to lutetium is called lanthanoid contraction. Yes, this is lanthanoid contraction, and lanthanoid contraction is due to the poor shielding of 4f electrons. Okay. Zirconium and hafnium has identical radii of 160 picometer and 159 picometer respectively as a consequence of lanthanoid contraction. Yes, this is absolutely correct. Because of lanthanoid contraction, zirconium Zr and hafnium Hf have the same identical radii. Okay, so option D is also correct. Option D is also correct. The explanation is also given here. So let comes to question number 54. Question number 54 is very easy. It is asking that to which of the following series the transition element z is equals to 39 to z is equals to 48 belongs to. Okay, so we know from 3D series, it is from oxidation, from atomic number 21 to atomic number 30. 4D series from uh, atomic number 39 to atomic number 48, and similarly 5D series from atomic number 57. Then we have 72 to 80. This is our 5D series. So Z is equals to 39 to 48 belongs to 4D series. Belongs to 4D series. Option 2 is correct. Now let's come to question number 55. Question number 55 is asking, just a second. Camenophore on treatment with concentrated H2SO4 form a compound X which decompose explosively on heating fuming Y. Okay, so we have to identify the X and Y. So in D and F block, there are certain important topics, and reaction of camenophore and K2Cr2O7 is very important for the perspective of NEET. Okay, so let we have to write the electronic so we have to write the equation for camenophore on treating with concentrated H2SO4. So here is the equation. When we react camenophore with H2SO4, it will give Mn2O7. Here Mn is in plus 7 oxidation state, then H2O, then KHSO4. Here Mn is highly unstable because here here Mn is in plus 7 oxidation state. Here Mn is in plus 7 oxidation state. Okay, so this is our x. So this is our x. Mn is in our x. So the option 1 will be correct. Okay, but we will check further also. Now what is saying further? Now we have to heat x. Okay, so when we heat x means Mn2O7. When we apply heat to it, we will get MnO2 plus O2. MnO2 MnO2, here Mn is in plus 4 oxidation state and oxygen. So here Y is MnO2. So X is our Mn2O7 and Y is MnO2. So we have to learn these reaction and we can simply tell X and Y. So the correct answer is 1. Okay. The question number 56. Question number 56 is asking when lanthanoid element is heated with sulfur, then the compound obtained is. Okay. So we have to tell the compound obtained. So we know the common oxidation state for lanthanoid is plus 3. It can show oxidation state of plus 2, plus 3, plus 4, but the most common oxidation state is plus 3. Okay. So we will take our oxidation state as plus 3. So we can simply write Ln, then 3, and then sulfur. And here the generally the oxidation state of sulfur is 2. So we can simply cross multiply and we will get the formula. So what we will get? Ln2S3. Ln2S3, Ln2S3. Option 2 is correct. This is the shortcut tricks for making the formula. Okay, this is correct. So now let's come to question number 57. Okay, question number 57. Here, which of the following species act as a reducing agent? Okay, so we have to tell the species which can act as a reducing agent. Reducing agent means it itself get oxidized and reduce other. It can reduce other element or reduce other compound. Okay, so for this we have to write the electronic configuration. Okay, for the first, we will write for Ce plus 4, cerium plus 4. Here the electronic configuration is xenon, then 4f0. So it is an stable electronic configuration, so it can't act as reducing agent. So option A is incorrect. Then lutetium 3 plus. Here the electronic configuration is xenon, then 4f14. Here it is also present in a very stable electronic configuration, so it can also not act as a reducing agent. Now EU2 plus. Here electronic configuration is 4f7. So it can easily lose another electron to become EU3 plus. It can easily lose electron to become U3 plus. So it get oxidized and it can reduce other element or other compound. So it can act as a reducing agent. Let's check for option 4 also. C3 plus. When we write the electronic configuration for C3 plus, it has 4F1. So it can act as a reducing agent. It can oxidize to Ce4 plus. But it here we can see that Ce3 plus is a very stable oxidation state for cerium, then plus 4. So it is very hard for cerium to go for plus 4 oxidation state. Okay, so it can't act as a reducing agent. Okay, it can't act as a reducing agent. So the correct option is third. And now let comes to question number 58. Question number 58. Read the assertion and reason carefully to mark the correct options. Okay, so this is an assertion and reason type question. Okay, so the assertion is ionization enthalpy for early actinoids are lower than that of early lanthanoids. Yes, the assertion is right because the ionization enthalpy for early actinoids are lower. Early actinoids are lower. This is due to the very less energy difference between the electronic configuration of actinoids. Lanthanoids have also the very less energy difference between its electronic configuration, but actinoids has even very less difference. Okay. So the ionization enthalpy for early actinoids are lower than that of lanthanoid. This is definitely correct answer. This is definitely correct assertion. And the reason here is 4f electron are more effectively, sorry, 5f electron are more effectively shielded from the nuclear charge than 4f electron to the corresponding lanthanoids. Yes. The reason is also correct because the 4f electron are better, or you can say more effectively shielded than the 4f electron. Okay. So the this is true because the lanthanoid series, the 5f electron experience poor shielding from the nucleus compared to the 4f electron in lanthanoid series. So it leading it to easier removal of electron from the lower and ionization enthalpy. Okay, that's why the assertion is correct. And for uh, the reason explains that the 5f electron are more effectively shielded from the nucleus charge than the 4f electron. Yes, it correctly explains the assertion. So the reason assertion is correct, reason is correct, and reason is the correct explanation of assertion. This is true because the addition electron cell in actinoids provide better shielding for the 4f electron, result in a lower ionization enthalpy compared to the lanthanoids. Okay, I think it is clear. It is a very good question as well. So now let's come to question number 59. Question number 59 is asking which of the following is a D block element. Okay, so GD, here we know GD is an F block element, then HS is D block element, then ES is F block element, and then cesium, CS is S block element. So it is asking for D block element. So C, option C, oh, sorry, option number B, HS is correct because it is a D block element. HS Hafnium is a D block element, belongs to the seventh period of transition. Okay, now
Okay.
let's come to question number 16. Here, the question is which of the following pairs of ion have the same electronic configuration? We have to tell which of the following pairs have the same electronic configuration. Okay, so let's start with Cu plus and Cr2 plus. Okay, First of all, we have to write the electronic configuration for Cu2 plus. We know the electronic configuration of Cu2 plus is 4s1 3d 10. Okay, so it is written over there. Okay, 4s1 3d 10. Now here 2 plus is written, means 2 electron will be lost. 2 electron loss means 3d9. Okay. Now Cr2 plus, electronic configuration for Cr2 plus is, first of all we will write for Cr, means 4s1 3d5. Okay. Now when we lose 2 electron, it will become 3d4. Okay, 3d4. So the electronic configuration will be different here, because one is 3d9 and another one is 3d4. Okay, so now let's comes to B part. B part is Fe3 plus and Mn2 plus. Okay, so first of all we will write for Fe. Fe will be 4s2 3d6. Okay, now when 3 electron will be removed, it will become 3d5 argon and then 3d5. Okay, now the second one is Mn2 plus. For Mn2 plus, we know the electronic configuration will be 4s2 3d5. When we have to remove 2 electron, when 2 electron will be removed, it will become 3d5 only. So 3d5, here both have same configuration, which is argon 3d5, argon 3d5. Hence B will be our correct answer. Here B will be our correct answer. But let's check for C and D also. Cobalt 3 plus and nickel 3 plus. We know the atomic number of cobalt is 27, so it will become 4s2 3d7. When we remove 3 electrons, it will become 3d6. Okay, now another one is Ni 3 plus. The atomic number is 28. For atomic number 28, the electronic configuration will be 4s2 3d8. When we remove 3 electron from it, it will become 3d7. Hence 3d6 and 3d7 with argon will be different configuration. Okay, so now let's do D part. D part is scandium 3 plus and chromium 3 plus. Scandium 3 plus will be first of all 4s2, then 3d1 for scandium, and from chromium we can write 4s1 3d5. Okay, now if we remove 3 electron from scandium, it will become 0. It will only become argon here. Okay, now for chromium 24, we have to remove how many electron? We have to remove 3 electron. If we remove 3 electron, first will be removed from here and 2 from there, so it will become 3d3 with argon. So it will also roam. So our correct answer will be B. Okay. So now let's comes to question number 61. Question number 61 is, zirconium and hafnium have almost same equal atomic, almost equal atomic and ionic radii because of. So we know zirconium belongs to 2D series. Zirconium belongs to 2D series and hafnium belongs to 3D series. And we know from 2D to 3D series there is lengthenoid contraction. What is lengthenoid contraction? In lengthenoid contraction, we can say there is gradual decrease in atomic and ionic radii. And why this has happened? This has happened due to the increase in atomic number, and, and it is due to the poor shielding of 4f electrons. So due to the poor shielding of 4f electron, the the atomic radii which have to be increased when we go down the group, it will not increase up to that extent. So the zirconium and hafnium uh, are in different group, are placed in different group, but still they have the same atomic radii. And how this is possible? This is possible due to the lengthenoid contraction. Okay, so it is due to the lengthenoid contraction, option B. Okay, now question number 62 says that reactivity of transition element decreases almost regularly from scandium to copper because of, okay, lengthenoid contraction, regular increase in ionization enthalpy, regular decrease in ionization enthalpy, and increase in number of oxidation state. Okay, we know that scandium, just a second, we know that scandium to copper come in 3D series of transition element. Okay, and we know that while going from the left side of the periodic table to the right side of the periodic table, there is increase in ionization enthalpy. Okay, so when we go from scandium to copper, it will be harder for the element to lose the electron because there will be high ionization enthalpy. So if they can't lose electron, hence they can't participate in more reaction. So their reactivity will decreases. Okay, so reactivity will decrease, and this is due to the reason of regular increase in ionization enthalpy. Okay, so let's comes to question number 63. Question number 63. Okay. Question is, which of the following is not correctly matched with the given example? Okay. A, an element of first transition series which has the highest second ionization enthalpy copper. Okay. An element of first transition series with highest third ionization enthalpy zinc. Okay. An element of first transition series with lowest enthalpy of atomization zinc. Okay, and the last one is last element of third transition series is cadmium. Okay, so we know that the last element of transition series are zinc, then cadmium, and then mercury, Hg. So for the third transition series, it should be mercury over there. So the we have to match the incorrect option. So D will be our incorrect directly. But let's check the other options as well. Okay, the A part. A part is the element with the first transition series highest second ionization enthalpy. Okay, we know the electronic configuration of copper is 4s1 3d10. Okay, and second ionization enthalpy means first electron will be removed from 4s1, and then the next electron will be removed from 3d10. So it will be difficult and it requires more ionization enthalpy because we have to remove electron from a very stable fully filled d10 orbital. So it will be correct answer. Okay, it will be correct. And another is an element of first transition series with highest third ionization enthalpy is zinc. Okay, we know the electronic configuration for zinc is 4s2 3d10. For the first ionization enthalpy, we will remove electron from 4s, and for the second, we will remove from 4s also. For the third, we have to remove from 3d, and 3d is a fully filled, very stable electronic configuration. So it will require high ionization enthalpy. Okay, so the option B is also correct. We have to find the incorrect option here. Okay, and the C part is an element of first transition series with the lowest enthalpy of atomization. Okay, we know that zinc has an electronic configuration of 4s2 3d10, and from this we can tell there is no unpaired electron. Okay, so when there is no unpaired electron, there will be less metallic strength. So when there is less metallic strength, we can easily break down into atoms, and this enthalpy is known as enthalpy of atomization. So yes, so there will be no unpaired electron, hence there will be low enthalpy of atomization for zinc. Okay, so this option is also correct, but we have to told here is incorrect option. So that comes to question number 64. Okay. 64 is Cu plus ion is more stable in aqueous solution because, okay, the second ionization enthalpy of copper is less than the first ionization enthalpy. Okay. B is large value of second ionization enthalpy of copper is compensated by much more negative hydration energy of Cu plus aqueous. Okay. C is hydration energy of Cu plus aqueous is more negative than that of Cu plus aqueous. Okay. Then D is many copper Cu plus compound are unstable in aqueous solution and undergo disproportionation reaction. Okay. The last one is correct. That Cu plus is unstable, and the reaction is shown is here. Then Cu plus aqueous is unstable, so it will disproportionate. Means uh, one will go to a higher oxidation state and another one will go to a lower oxidation state. Okay, so here it is in +2 oxidation state and here copper is in 0 oxidation state. Okay, hence this is a disproportionation reaction, but it can't explain the reason. So hence D option is incorrect. We know that while going from copper plus to copper 2 plus, there is increase in ionization enthalpy, but the correct option will be B. Here the option B will be correct because there will be high ionization energy for Cu2 plus, yes, but it will be stabilized by the hydration energy. It will be stabilized by the large negative hydration energy of Cu2 plus. Okay, so the correct answer will be B. Okay, now let's comes to question number 65. Question number 65. Identify the species in which metal atom is in plus 6 oxidation state. Okay, so we have to find the oxidation state. Okay, so we can take the oxidation state of MnXX, and then for we know the oxidation state for each oxidation atom will be -2, so -8 and -1 on the right hand side. So X for the first will be +7. So it is wrong. Then for second, for chromium we can write X. Then for each Cn we can write -6 and then -3. Okay. So X will be +3. So B option is also incorrect. For C, let's check here. For nickel, I can assume X. Then for each fluorine, -6 and equals to -2, as X equals to -4. So option C will be also wrong. So for D, we can take chromium as X. Then for each O, there will be 2 into 2 means 4. And for each Cl, -2 equals to 0. So X here equals to 6. So the correct option is D. Here the chromium atom is in +6 oxidation state. Okay. That comes to question number 66. Um, in which of the following pair of ion the higher oxidation state in aqueous solution is more stable than the other? Okay, here we have to tell the higher which of the following higher oxidation state in aqueous is more stable than the other. Okay, so here we have to check for titanium to titanium 3 plus, then we have to check for copper to copper 3 plus, copper 2 plus, then for chromium to chromium 3 plus, then vanadium 2 plus to VO 2 plus. Okay, first of all we will check this by electronic configuration concept. More stable electronic configuration means it will be more stable in aqueous as well. Okay, so for titanium we can write electronic configuration as 4s2 3d2. Okay, and for another is titanium 3 plus. For titanium 3 plus we can write 4s2 3d2, then 3 electron will be removed, so only 3d1 left. So hence here one is a fully filled orbital. So titanium will have more stable electronic configuration. Okay, so this will our incorrect answer. Titanium 3 plus is less stable than titanium. Okay, so for copper to copper 2 plus, okay, we know that copper to copper 2 plus is more stable. We can say because of hydration energy, as we have discussed earlier, and we can also say that with a higher positive charge it will more stable in aqueous solution. Okay, so we can explain this by these two concepts. Okay, so now we will check for option 3, which is Cr2 plus and Cr3 plus, and we know that chromium is more stable in +3 oxidation state, so it will be correct. Okay, so because chromium preferred to be attain a +3 oxidation state due to stability reasons, yes, because chromium is more stable in +3 oxidation state than Cr2 plus. Okay, and the last one is vanadium 2 plus to VO 2 plus. Okay, and vanadium also prefer to be in higher oxidation state. Okay, so here vanadium oxidation state is in +2 and here it is in 4 plus, because X minus 2 is equals to 2, X is equals to 4. So vanadium is in higher oxidation state in VO2 plus, hence it will be also correct. Okay, so our correct are options are 2 3 and 4. So 2 3 and 4, option D will be correct. Okay, option D will be correct. So now let's comes to next question. CuSO4 is paramagnetic while ZnSO4 is diamagnetic because, okay. So first of all, we can separate them. CuSO4 as Cu2 plus and SO4 2 minus. Okay, and same for the zinc. ZnSO4 Zn2 plus SO4 2 minus. Okay, so now we will calculate the electronic configuration for Cu2 plus. For Cu2 plus, we can write 4s1, then 3d10, and then 2 plus. For 2 plus, we can say 3d9. So for 3d9, when we draw the orbital diagram, we can find that it is paramagnetic in nature. Okay, so Cu2 plus will have an unpaired electron, so it will be paramagnetic. For Zn2 plus, we know the electronic configuration for Zn will be 4s2 3d10. Okay, so when we remove 2 electron from it, it will become 3d10. Okay, so the d orbital is fully filled, so we can say that there is no unpaired electron. When there is no unpaired electron, it will be diamagnetic. Okay, so the correct option will be Cu2 plus is in 3d configuration, while Zn2 plus will be in 3d10 configuration. Okay, it will be in 3d9 configuration. Okay, it will be in 3d9 configuration. Now let's comes to question number 68. Which of the following transition metal has the highest magnetic moment? We know that we can calculate magnetic moment by the formula mu is equals to under root n into n plus 2. Okay, and here n is the number of unpaired electron. So we have to calculate the number of unpaired electron from each of the following. The one which has the more number of unpaired electron will have the higher magnetic moment. Okay, for Cu2 plus, I am directly writing the configuration here. It will have 3d9. For nickel, we can say 3d8. For cobalt, we can say 3d7. And for iron, it will be 3d6. So here uh, let me show for 3d9, 1, 2, 3, 4. Okay. So 3d9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here the number of unpaired electron is 1. Okay. For 3d8, the number of unpaired electron will be 2. For 3d7, the number of unpaired electron will be 3. And similarly for 3d6, the number of unpaired electron will be 4. So the Fe2 plus will have higher magnetic moment because it has the highest number of unpaired electrons. Okay. Um, so the correct option will be D. So now let's comes to question number 69. Okay, which of the following transition metal ion is colorless? Okay, so we can say the metal ion will be colorless when there will be no unpaired electron. Okay, so when there will be no unpaired electron, then it then they can't show DD transition, and when they can't show DD transition, there will be no color in the compound. Okay, so vanadium 2 plus. Vanadium 2 plus, you can say scandium titanium vanadium means atomic number 23. So we will remove 2 electrons, so it will become 3d3. Okay. For chromium 3 plus, chromium 3 plus electronic configuration for chromium is 4s1 3d5. Okay. So it will also become 3d3. Okay. Now for zinc 2 positive, it will become 3d10. So and for titanium 3 plus, it will become 3d1. Okay. For zinc 2 plus, here the electronic configuration is 3d10, means there is no unpaired electron in d orbital as it is fully filled. Okay, so when there is fully filled, there will be no unpaired electron. When there will be no unpaired electron, there will be no dd transition, and when there will be no dd transition, then there it will be colorless. Okay, colorless. So the correct option will be C, zinc 2 positive. Okay. So now let's comes to question number 70. Okay, question number 70. Question number 70 is a theoretical question. Okay, which of the following actinoid element is not found in nature? Okay, so here we know that thorium, yes, it is found in nature. Okay, then atomic number 91 is Pa. Yes, this is also found in nature. And then uranium is also found in nature. But the atomic number 103, lorcinium, it is a synthetic element which is generally prepared in the laboratories. Okay, so it is a synthetic element that is not found in nature. So our correct option will be 4. Okay, it is synthetic and not found in nature. So now let's comes to question number 71. Question number 71 is which order is correct for oxidizing power? Oxidizing power. Okay. The compound will have the more oxidizing power when it will be in its highest oxidation state. Okay. जब वो अपनी highest oxidation state में होगा तो वो जो है खुद तो reduce हो जाएगा. It will be it himself got reduced, but it will oxidize the other. It will oxidize the other element, hence it will have higher oxidizing power. Okay, so we have to check which of the following is in its highest oxidation state. Okay, so let's check step by step. For option 1, here we can calculate the oxidation state of chromium is in +6. Okay, let me show. 2x minus 14 is equals to minus 2. So 2x is equals to 12 and x is equals to 6. So here chromium is in +6 oxidation state and vanadium 2 plus. So it will be in +4 oxidation state. So chromium is in higher oxidation state. So this will is wrong answer. Then similarly for this, vanadium x minus 4 is equals to 1. So here vanadium is in +3 oxidation state and Mn is in +7 oxidation state. So here it is also wrong answer. Then option C. Similarly, this has +3 oxidation state, and it will have +6 oxidation state. Okay. So the option C will be correct. And let's check option 4 also, that 2x. Here we can also calculate it is in +6 oxidation state, and here Mn is in +7 oxidation state. So but the arrow is in that side, so the option 4 is also wrong. So hence we can conclude that option 3 is correct, because here chromium is in its highest oxidation state, that is in +6. So it has the highest oxidizing power. Okay. The same explanation has been given here. So now let's comes to question number 72. Which of the following, which compound is used in the manufacturing of K2Cr2O7? Okay. So here is the equation for preparation of K2Cr2O7. Okay. First of all, we will start with FeCr2O4. Then it will become Na2CrO4. Then uh, we have to do the reaction of Na2CrO4 with H plus, or you can say acid. Then we will get Na2Cr2O7. Then from Na2Cr2O7 we will get K2Cr2O7. From Na2Cr2O7 we will get K2Cr2O7. Okay. So the correct option for the manufacturing of K2Cr2O7 will be FeCr2O4, because we have to start the reaction with FeCr2O4. Then we will get Na2CrO4. Then from Na2CrO4 we will get Na2Cr2O7. Then from it we will get K2Cr2O7. So the correct option will be C. Okay. Now the question number 73. Question number 73 is where the general electronic configuration for of lanthanoid element is. So we have to tell the general electronic configuration from for the lanthanoid element. Okay. So the general electronic configuration for lanthanoid will be 6s2 and for 5D it will be 0 to 1, and then for lanthanoid it will be 4f, and for f it will be 1 to 14. So this is the general electronic configuration for lanthanoid. Is it matching? No, option 1 is incorrect, 2 is incorrect, option 3 is also incorrect. So option 4 is correct. Okay, none of these is the correct answer. Okay, none of these is correct answer. And the correct electronic configuration is uh, yes, xenon, and then 6s2, 5d0 to 1, and then 4f1 to 14. 4f1 to 14, 5d0 to 1, 6s2. Okay, this is our correct answer. So now let's start question number 74. If the magnetic moment of an ion x raised to power of n plus is root 24 Bohr magneton, what is the number of unpaired electrons and the oxidation state n of the element with atomic number 26? Okay, so we have given with the mu, that is magnetic moment root 24, and we know that magnetic moment mu is equals to number of n into n plus 2, where n is the number of unpaired electron. Okay, so we want the value to be 24. So if we put n is equals to 4, if we put n equals to 4, root of n into my 6, so we get 24. Hence our magnetic moment is equals to 24. So this condition is satisfied. Now the atomic number is 26 is given. So this atom will be iron. Now we want the oxidation state on which this magnetic moment can be achieved. Okay. So first of all, we will write the electronic configuration of iron. So it will be equals to 4s2 3d6. And now we want 4 unpaired electron, because then only we will get our mu is equals to 24. So first of all, let's draw the diagram. 1 2 3 4 5, this is d orbital, and I am putting first d6 electron in this. 1 2 3 4 5 6. Now I have 4 electrons. Now I have 4 unpaired electrons, and this will be enough for getting the magnetic moment to be root 24. So I don't want these two electron for this, so I will remove this. So the iron, it will become Fe2 plus. In Fe2 plus it will become 3d6, and we have 4 unpaired electron, and magnetic moment will be equals to root 24. So the correct answer will be 4 comma 2, because 2 will be the charge. Okay, so I think this question will be clear. Now 75, the transition element have a general electronic configuration. So this is a very basic question. Here we have to write the general electronic configuration for the transition element. So it should be ns, ns, and then just a second, 75, ns 1 comma 2, and n minus 1, d 1 to 10. So we know this is the general electronic configuration for all the transition element for 3D, 4D, and 5D series. Okay, so this is clear. The correct option will be n minus 1. The correct option is C. Okay, so now let goes to question number 76. Okay, question number 76 is saying, which of the following element is not a member of transition element? Okay, so we have to find which of the following is not a transition element. First is hafnium. So it belongs to 5D series, your third transition series, 5D series. And then PT, this also belongs to, platinum also belongs to 5D series. And then cerium, this belongs to lanthanoid series. This belongs to lanthanoid series. Okay, and then molybdenum, this belongs to belongs to 4D series. 4D series of transition element. 4D series of transition element, 5D series of transition element, 5D series, and this CE belongs to lanthanoid series. So our correct answer will be C, because we want the incorrect answer. Okay. So let's come to question number 77. Question number 77. The number of unpaired electron in gaseous species of Mn3 plus, Cr3 plus, and V3 plus respectively are. Okay. So so first we will write the electronic configuration, then we can easily check. Okay. So let's look at the solution. Mn3 plus. We know the electronic configuration for Mn will be 4s2 3d5. For Mn will be 4s2 3d5. Now we want 3 plus. So we can first the 4s electron will be removed and then one electron from 3d will be removed. So it will become, and here argon is also there. Okay. So the d4 will be left. Okay, d4 will be left, so we can draw d4 through this diagram. So the number of unpaired electron will be 4. Now cr3 plus, first we can write the configuration for cr, which is 4s1 3d5. Now for 3 plus we can remove 1 from s and 2 from d, so it will become d3, d3, 3d3 you may say. Now, so unpaired electron will be 3. Now similarly for vanadium, we can find, first we will write the configuration from vanadium. This will be scandium, titanium, vanadium. So 4s2, 3d3. Now we will remove 3 electrons. So 2 electron from this and 1 electron from this. Now this will d2 will become. Now unpaired electron will be 2. And what question says, the number of unpaired electron. So Mn has 4, then 3, then 2. 4, 3, 2. So C is the correct answer. Okay, C is the correct answer. I will change it. This, okay, this is the correct answer, B. Okay. Now next question is 78. Next question 78 is saying which form colored salt. Okay, which of these four form the colored salt, means which of the following shows the color. Okay, this is the basic question. The first is non-metal, second is metal, third is p block elements, and then transitional element. Okay, so we know transition elements show color both in solid and aqueous solution because they have incomplete d orbitals. If they have incomplete d orbitals, then they will have unpaired electron. Then they will have unpaired electron. And when they have unpaired electron, these electron will go under dd transition and emit color. dd transition. dd transition and show color. Okay. So this will be clear. The correct answer will be transitional element because they have incomplete d subshell, or you may say they will be have unpaired electron in their d or d subshell, and then these unpaired electron will go under dd transition and the color will be shown. Now question number 79. Zinc and mercury do not show variable valency like d block element because, okay, first they are soft, their d subshell are complete, they have only two electron in the outermost subshell, their d subshell are complete. Okay, so we can write their electronic configuration, then we will look in this. So first of all we can write for zinc 4s2 3d10. Similarly for cadmium and mercury, they will also have fully filled 4s and fully filled d orbital. Okay, so when they have fully filled d orbitals, hence they can't show variable oxidation state. Okay, so the correct answer is B because their d subshell are complete. Now come to question number 80. Transition element form color ions due to. Okay, transition element form color ion due to because transition element show variable oxidation state, so they have unpaired electron. So they have unpaired electron. So these unpaired electron will go under dd transition, go under dd transition, dd transition and show color. Okay, so transition element form colored ion due to dd transition because there is splitting of energy levels of d due to the presence of ligands. So they don't remain degenerate, means they don't have equal energy now. Okay, so they show color due to the dd transition. Okay. Now let's comes to question number 81. Which of the following transition metal ion is colorless in aqueous solution? So we have to tell which metal ion is colorless in aqueous solution. So we know the metal ion will be colorless which don't have unpaired electron. If it will have unpaired electron, then it will show color. If it don't have unpaired electron, then no color will be shown. So first we will check for titanium 4 plus. Titanium 4 plus. Electronic configuration will be 4s2, 3d2. For zinc 2 plus, for titanium 4 plus, these two electron will be removed and these two electrons will be removed. So outermost electronic configuration will become 4s0, 3d0. Means it don't have electron, both zero. Hence it don't, so it will not show color. Because for showing color, it must have unpaired electron. So this is not our answer. Now zinc 2 plus. Zinc 2 plus will have 3d10 in its outermost shell. So in 3d10 configuration, this will also not show color because there will be no unpaired electron. Okay. Now V4 plus, यानी कि vanadium 4 plus, vanadium 4 plus, 4s2, 3d3. So when we remove 4 electron from this, these 2 electron will be removed, then these 2 electron will be removed. So it will become 3d1. So there will be one unpaired electron, so it will show color. And it is asking for colorless. So colorless will be A and B. So D is the correct answer because both A and B will not show color. Okay. Now question number 82. Cuprous ion is colorless while cupric ion is colored because, okay, both have half filled p and d orbital. Cuprous ion has incomplete d orbital and cupric ion has a complete d orbital. Okay. Both have unpaired electron in the d orbital. Okay. Cuprous ion has complete d orbital and cupric ion has incomplete d orbital. Okay, for showing color and colorless, we can just answer it by using the concept of unpaired electron. If it will have unpaired electron, then it will show color. If it don't have unpaired electron, then no color will be shown. Okay, so we will do the same here. Here Cu plus. First we will write the electronic configuration for Cu plus. For Cu the electronic configuration is 4s1 and then 3d10. So one electron will be removed from 4s, then it will become 3d10. So there is no unpaired electron, so no color will be shown. Okay. Now for Cu2 plus, the electronic configuration, one more electron from the 3d subshell will be removed. So the electronic configuration will become argon, then 3d9. So it will have one unpaired electron, so it will show color because that unpaired electron can go under dd transition and show color. Okay, so correct answer will be cuprous ion has complete d orbital and cupric ion has incomplete d orbital. Okay, so now let comes to question number 83. In first transition series, the melting point of manganese Mn is low because, okay, the melting point of manganese is low. uh, it has D5 configuration. Manganese has D5 configuration in its outermost shell, but still it has low melting point. This is because the half-filled 3D subshell result in a specific arrangement that does not favor strong metallic bond. Due to that 3D geometry of D5 configuration, due to the specific arrangement, the manganese can't show higher melting and boiling point. Okay, that's why manganese has a lower melting point due to the geometry and arrangement in the 3D space. So it will have a weak metallic bonding. Okay. So the correct answer will be due to D5 configuration, metallic bonds are weak. Okay. Now question number 84. Assertion and reason type question. Transition metals show variable valencies. Yes, this is absolutely right. Transition element shows variable valencies. Transition element have a large energy difference between ns2 and n minus 1d electron. So it is saying that ns2 and n minus 1d in transition elements have large energy difference. Okay. So first assertion is absolutely right because transition elements show variable valencies. This is absolutely right. Now we have to tell whether the reason is correct, and it is correct explanation also of assertion. So the reason is wrong because it is saying large energy difference. But ns2 and n minus 1 in transition series have a very less energy difference. Due to this very less energy difference, this statement is wrong. Reason is wrong, so our correct answer will be assertion is correct and reason is incorrect. So option C is correct. Okay. Okay. So now let's start question 85. Which of the following arrangement does not represent the correct order of the property stated against it? Okay. So we have to tell the incorrect option. Okay. The incorrect property. Okay. So the first one is paramagnetic behavior. We have to tell about the paramagnetic behavior of V2 plus means vanadium 2 plus, chromium 2 plus, manganese 2 plus, and iron 2 plus. Okay. For telling about the paramagnetic behavior, we will first calculate the number of unpaired electron. So more number of unpaired electron will be there. So the higher paramagnetic behavior it will show. Okay. For solving this, we will calculate the electronic configuration for all the given elements. Okay. Here we have given with vanadium, chromium, manganese, and iron. Okay. So we will write their electronic configuration. For vanadium, it will be 4s2 3d3, chromium 4s1 3d5, manganese 4s2 3d5, iron 4s2 3d6. Then we will remove the number of electrons that was stated in the charge. Okay. So it has 2 plus charge means 2 electron from 4s will be removed. Okay. So for 3d3, the diagram will be look like this. Okay, one electron, two electron, three electron. So there will be three electron, and all threes are unpaired electron. Okay. Similarly, in chromium we will have four unpaired electron. In manganese we will have five unpaired electron, and in iron we will have four unpaired electron. Okay. So the paramagnetic behavior is almost correct here. Okay. And then we will check for ionic radii. Okay. Ionic radii. And we know generally the ionic radii decreases as the atomic number increases in a particular transition series. Okay, because we know when we go from the left side of the periodic table to the right side of the periodic table, there will be decrease. There will be decrease in size. Okay, there will be decrease in atomic radius, and there is no exception given in the following element. Okay, so when we increase the atomic number, their radii will decrease. So this is also the correct option. Now we have to tell about the number of oxidation state. Okay, we have to tell about the number of oxidation state. We know the oxidation state for scandium will be plus 2 and plus 3. Similarly for titanium plus 2 plus 3 and plus 4. Then for chromium it will range from plus 2 plus 3 plus 4 plus 5 to plus 6. And from manganese it will range from plus 2 to plus 7. Okay, so the order is correct. And here we are asked with the incorrect property. So the first one is incorrect. The first property is incorrect. So our correct option will be A. Correct option will be A because first one is incorrect. Okay. So now let's come to question number 86. Which of the following ion will exhibit color in aqueous solution? So we know the color will be executed by the compound uh, which will have unpaired electron. Okay. So when it will have unpaired electron, it will go in DD transition and it can show color. Okay, so first of all, we will write the electronic configuration, then we will calculate the unpaired electron. Okay, so for lanthanum, we will have 54 electron, so it will be equivalent for lanthanum 3 plus. So it is equivalent to noble gas configuration of xenon. Similarly, for titanium 3 plus, we will have 19 electron and we will have one unpaired electron, so it will be colored. Okay, so then we have Lu 3 plus, it has 68 electron and a fully filled f orbital. So there is no unpaired electron, hence no color will be shown. Similarly, for scandium 3 plus, it has 18 electron, which is similar to argon. So no unpaired electrons means no color. So the uh, correct answer will be titanium. Okay, option B. Now let's come to question number 87. For the D block element, the first ionization potential is of order. Okay, so we will have to calculate the ionization enthalpy. Okay, we can calculate ionization enthalpy normally just by saying that when we go from the left side of periodic table to right side of periodic table, there will be increase in ionization energy. Okay, but there are some irregular trends also in D block element, so we will have to check by calculating the electronic configuration. Okay, so we will write the electronic configuration for each element. Here we have write for zinc, then for iron, then for copper, then for chromium. Okay, and now it is asking the order. Okay, so here we can um, mm, see that it has 4s1 and it has 4s1. Okay, so it will be hard for chromium. We require more energy for we require less energy for chromium because we will have 4s1 and it has half filled stable d5 orbital. Okay, so chromium has the least. Okay, chromium has the least. Then we will have copper because it has 4s1, no fully filled 4s subshell, but it has fully filled D subshell. Okay, so that's why copper. And then iron, because here D subshell is not fully filled. Then we will have zinc because it has fully filled 4s subshell and 3D subshell. Okay, here we have 3D. Here we have 3D. 3D subshell. 3D subshell. 3D subshell. Okay. So now let's come to next question. The correct answer will be A. Question number 88. Which of the following statement is incorrect? So again we have to tell the incorrect statement. Okay. A is zinc, cadmium, mercury due to the presence of completely filled d orbital are not transition metal. Okay. And another second statement is zinc, cadmium, mercury have low melting point and are comparatively soft than other transition metal. Okay. Third statement is metallic bond made by elements with D5 configuration is stronger as compared to metallic bond made by elements with D3 configuration. Okay. Then we will have last statement as metal of 5D series form strong metallic bond as compared with the metal of 3D series. Okay. So now we have to tell the incorrect statement. The first statement is fully correct because zinc, cadmium, mercury have completely filled d orbital. That's why they are not considered as transition element. This is correct. And zinc, cadmium, mercury, so they don't have unpaired electron. That's why they have low melting and boiling point. So that's why they are soft than other transition metals. So this statement is also correct. And third statement is that D5 configuration is stronger as compared to metallic bond made by D3 configuration. This is wrong. And this is, you can say, an exception because in D5 configuration, the arrangement of D5 configuration in such a way that it can't form strong metallic bonds due to its 3D geometry. Okay, that's why 3D configuration has more metallic strength. Okay, because D5 has not that structure which support higher magnetic bond strength. So this statement is incorrect. And then D part, metal of 5D series forms strong metallic bonds as compared with metal of 3D series. This statement is definitely true because 5D series elements have large atomic mass, large atomic number. So that's why they form strong metallic bonds. The metallic bond made by the elements with D5 configuration is weaker than the D3 configuration. Okay. So third statement is wrong. So the correct option will be C. because we are asked with the incorrect one. Now question number 89. A reduction in atomic size with increase in atomic number is a characteristic property of element of. Here we will have property. Okay, characteristic property of. So it is a characteristic property of F block element. It is a very famous line from NCRT that a reduction in atomic size will increase in atomic number is a characteristic property of F block element due to the lanthanoid and actinoid contraction. So it is a very easy theoretical question. Now let's come to question number 90. The approximate percentage of iron in mish metal is. Okay. So mish metal is an alloy which formed by a combination of many metals. So mish metal contain about 94 to 95% of rare earth metal, or you can say lanthanoids, and it has 5% of iron, and it has some traces of sulfur, carbon, silicon, calcium, and aluminium. So we are asked with the percentage of iron. So it has 5% iron. Okay. So let's comes to question number 91. Which of the following exhibit the minimum number of oxidation state? So we have to find the minimum number of oxidation state. Okay. So we know the manganese can show oxidation state from +2 to +7 as we have discussed earlier. And NP can exhibit oxidation state from +3 to +4, +5 and +6. It can exhibit 4 oxidation state. Okay. Thorium can exhibit +4 and +3, but the most common uh, oxidation state is +4. The most common and most stable is +4. +3 is very rare, you can say. Okay, and chromium is +2, +3 to +6 also. +2, +3, sometime +4 also. Okay, so the correct answer for the minimum number of oxidation state will be thorium, which is option C. Okay, so it has normally oxidation state of +4, but it can show +3, but which is not very stable. Most stable is +4. So that's why thorium has minimum number of oxidation state. So now let's come to question number 92. We have the some given statement. First one is LaOH whole thrice is the least basic among the hydroxide of lanthanoids. Okay. The second one is zirconium 4 plus and hafnium 4 plus possess almost the same ionic radii. Okay. And Ce4 plus can act as an oxidizing agent. Okay. So we have to tell the correct statement. Uh, Here we will have that lanthanum OH whole thrice. This is the not least basic, it is most basic. It is most basic. Okay. This is not least basic, this is most basic. So this is incorrect. Zirconium 4 plus and hafnium 4 plus possess almost same ionic radii. Yes, this is uh, exactly correct because it is due to the lanthanoid contraction. Due to the lanthanoid contraction, zirconium 4 plus and hafnium 4 plus possess almost same ionic radii. Okay, so this is correct. And Ce4 plus can act as an oxidizing agent. This is also correct because Ce4 plus can go to a more stable state which is Ce3 plus. So it will get reduced and it will oxidize the other element or you can say other compound. So it can act as an oxidizing agent. So correct is second and third. So correct option will be B. Okay. So now come to question number 93. Lanthanum is grouped with F block element because. Why is lanthanum is grouped with F block element? The lanthanum is uh, grouped with F block element because lanthanum doesn't have the partially filled F orbital. Lanthanum doesn't have the partially filled F orbital. So correct answer is A. So the correct answer is A. Correct answer is A. Because the lanthanum has partially filled F orbital. Okay, so now comes to question number 94. Question number 94 states that large number of oxidation states are exhibited by the actinoid than those by the lanthanoid. What is the main reason behind this? Okay, so the main reason is there is a less energy difference between 5f and 6d than 4f and 5d orbital. We have learned earlier that 4f and 5d has less energy difference. That's why 3d series, or you can say transition elements, show variable oxidation state. This is correct. But actinoids, the actinoids and the 5f and 6d has even less difference in their energy. Okay, so they exhibit more number of oxidation states. So the correct answer is B, which is less energy difference between 5f and 6d than 4f and 5d. Okay, the same has been written here. So now comes to question number 95. Although plus 3 is the characteristic oxidation state for lanthanoid, but cerium also show plus 4 oxidation state because, okay, cerium also show plus 4 oxidation state. Why? It has a variable ionization enthalpy. No, it don't have variable ionization enthalpy. Second is it has a tendency to attain a noble gas configuration. We can check it by writing the electronic configuration. It has a tendency to attain F0 configuration. We can also check this by electronic configuration. It resembles P4, PB plus 4. Okay, so let's check by writing electronic configuration. So the electronic configuration for Ce3 plus will be xenon, then 4f1. Okay. So when we write for Ce4 plus, one more f electron will be removed. So it will become xenon and then 4f0. So it has a stable noble gas configuration. B option is absolutely right. It has a tendency to attain F0 configuration. Yes, in Ce4 plus it has F0 configuration. So option 2 is correct, but it doesn't resemble to PB plus 4 electronic configuration. So the correct option are 2 and 3. So A is the correct option. So now let's come to question number 96. Question number 96. This concept is generally we study in covalent bonds. So first is we have to tell which of the following is paramagnetic. Paramagnetic means which of the following has unpaired electron. Okay. So we will check from here. O2 2 plus. Okay, so oxygen here will have even number of electron. When we remove even number of from even number of electron, when we remove plus 2 electron, we still have even number of electron. When we will have even number of electron, then there will be no unpaired electron. Okay, so it will not show paramagnetic behavior. Similarly, we can say uh, S2 2 minus will have even number of electrons, so it can't have unpaired electrons, so can't show paramagnetic behavior. Similarly, N2 has 14 electron, N2 has 14 electron which is even in number, so no unpaired electron. No unpaired electron. Now, uh, option number 4. Okay, option number 4 is B2. So here boron has 10 electron, but it is an exception. It is an exception. We have to remind it. We have to remember it that it has even number of electron, but still it is paramagnetic in nature. This is because it has two unpaired electron in its pi 2px and pi 2py molecular orbital, which makes it paramagnetic in nature. So it is an exception which has 10 electron which is even in number, still it is paramagnetic in nature. Okay. Now comes to question number 97. Question number 97 states that cerium is an important member of the lanthanoid. Which of the following statement about cerium is incorrect? Okay, we have to tell the incorrect statement. Cerium plus 4 can act as oxidizing agent. Yes, this is correct because cerium plus 4 can goes to cerium plus 3, which is more stable, okay, so it can act as oxidizing agent. Another one is the plus 3 oxidation of cerium is more stable than plus 4. Yes, this is absolutely correct. plus 3 is more plus 3 is more stable, and then plus 4 state of cerium is not known in solution. No, it is known in solution. Plus 3 is more stable, but plus 4 oxidation state is also occur in solution in aqueous form, you can say. And the most common oxidation state for cerium is plus 3 and plus 4. This is correct. So the incorrect one is option number C, which is the plus 4 oxidation state of cerium is not known in solution. Now question number 98. La3 plus and Lu3 plus ion are colored in solid state and in aqueous state. This is our assertion. This is an assertion reason question. And the reason is the color of lanthanoid ion may be attributed to the presence of F electrons. Okay. So here in assertion we can say lanthanum 3 plus and Lu 3 plus are not colored in solid and aqueous because they don't have partially filled F orbital in its ground state. They don't have lanthanum 3 plus and Lu 3 plus. When we calculate their electronic configuration, they don't have partially filled partially filled F subshell. So when they don't have partially filled F subshell, they can't show color in solid and aqueous state. So the assertion is incorrect. We can easily calculate by writing its electronic configuration. Okay, and the reason is color of the lanthanoid ion may be attributed to the presence of F electron. Yes, this is absolutely correct because the color of the lanthanoid ion will be shown by the unpaired F electrons. When there will be unpaired F electron, it will show color. Okay, so this is correct. We can also read from here. The assertion is false because lanthanum 3 plus and Lu 3 plus ion are not colored. They are colorless due to the absence of partially filled F orbitals. The main reason is due to the color in the lanthanoid ion is indeed due to the presence of F electron. Okay, so they don't have partially filled F electron, so that's why the assertion is incorrect. But the reason is correct, so option 4 will be correct. Assertion is false, but the reason is true. Question number 99. Okay. Question number 99 states which of the following ion exhibits DD transition and paramagnetic as well? Means we have to find the unpaired electron. Okay. So the compound which will have unpaired electron will definitely show DD transition. Okay. There are some exceptions, but they are very few. Okay. So when we have unpaired electron, when we have unpaired electron, it will undergo dd transition, and it will show color. Okay, so we can check by writing this. So first of all, for we will have to write their electronic configuration. For the chrome CrO4 2 minus will be X minus 8 is equals to minus 2. Okay, so here chromium is in plus 6 oxidation state. Chromium is in plus 6 oxidation state. When chromium will be in its plus 6 oxidation state, so it will not have any d it will not have any you can say unpaired electron or no partially filled d substrate. Okay, so this is not our answer. Similarly, we can check for Cr2O7 2 minus. For Cr2O7 2 minus, we can 2x minus 14 is equals to minus 2. Here also we get x is equals to 6, means in second part also chromium is in plus 6 oxidation state. So in plus 6 oxidation state, it will not have partially filled d subshell, so it will not have unpaired electron, so it will not go under dd transitions, means it will not show color. Okay, and for C part, we will have MnO4 2 minus. For MnO4 2 minus, means x minus 8 is equals to minus 2. Here x is in plus 6 oxidation state. Here x is in plus 6 oxidation state. So Mn6 plus. Mn6 plus will definitely have an unpaired electron. We can draw its diagram. That Mn has an electronic configuration of 4s2 3d 5. When we remove 6 electron from this, means 2 electron will be removed from here and 4 electron will be removed from here. So it will become 3d1. So when it will become 3d1, it will have an unpaired electrons, mean it will show color. Okay, and similarly for the last D part, we will have Mn of O4 minus, means it will be in +7 oxidation states, means no unpaired electron. Okay, so the correct option is C. So now let comes to last question, which is question number 100. Formula of halide of lanthanoid may be. So we have to calculate the formula for halide. This is very basic. We know the basic oxidation state shown by lanthanoid is +3. Basic oxidation state shown by lanthanoid is +3, and halogens such as fluorine, chlorine, bromine, iodine show +1 oxidation state, or you can say it will show -1 oxidation state. Okay, -1 oxidation state. So lanthanum, and here is halogen. So it will have 3. It will have. So we will simply can cross multiply and get this lanthanum x3. So the answer will be LaX3. LaX3. Option 1 is correct. Okay. The general reaction is represented here. I have also tell the shortcut method for this. Okay. So here we have completed our lecture. So thank you so much.